Okay, radicals. This is a review from last year. So complete the following. 7 times 7 equals 49, so the square root of 49 is 7. But negative 7 times negative 7 is also 49, so another square root of 49 is negative 7. So basically what they're saying is when we square 7 or negative 7, the result for both of them is 49. And so whenever we take the square root of a number, it can equal the positive or the negative. And so that's something we never really talked about in grade 10. So the number 49 has two square roots, one positive and one negative. The positive is what we call the principal square root, and the negative is what we call the secondary square root. Every possible number has two square roots, a principal and a secondary. Okay, as long as it's in an even index. Remember, the index is so if we're doing the square root or the fourth root or the sixth root. The square root of a perfect square are rational numbers. So square root of 36 are 6 and negative 6. The square root of non-perfect squares are irrational numbers. Remember, irrational means you cannot write as a fraction. So irrational cannot be. So all square roots that we can't, that don't give us a whole number or an integer when we square root it, then they're irrational. So cube roots, 3 times 3 times 3 equals 27. So the cube root of 27 is 3. Negative 3 times negative 3 times negative 3 is actually equal to negative 27, not 27. So the cube root of negative 27 is negative 3. So all numbers, positive and negative, have only one cube root. So cube root of 1,000 is 10. Cubic root of a negative 8 is negative 2. So the cube root of a non-perfect cube is also an irrational number. So next page. So let's review without using a calculator. So you have to memorize a lot of these. So a square root of 64 is 8. Square root of negative 64 is not possible, right? Undefined. We cannot take the square root of a negative. We can take the cube root, but not the square root. Negative root 64 is the same thing as negative times 8 or negative 8. Cubic root of 64 would be, so this is cubic root. So that's 4. 4 times 4 times 4 is equal to 64. The cubic root of negative 64 would be negative 4, since negative 4 times negative 4 times negative 4 equals negative 64. And the last one is the negative cubic root of 64, so we have negative times 4 or negative 4. So on your calculator, if we grab that out, just got to close this, sorry. You grab your calculator. Let's review where these buttons are. So on our calculator, the square root button is second x squared. Second x squared. And the cube root is math number 4. Math 4. So that's where we find those buttons. So this first one, the cubic root of 729, I push math 4, 729, and that gives you 9. Square root of 196, I would go second x squared, 196. That gives me 14. Okay, the cubic root of 512 over 343. So math 4 for cubic root. 512 divided by 343 and close my bracket. And so if we go math, answer, enter to see if that can be reduced. Yeah, and it's 8 over 7. Evaluate to the nearest hundredth. Remember, hundredth is 2 decimal places. 2 decimal places. So in our calculator, second of the x squared button, so square root of 52, 7.21. And the cubic root of 71, so math 4, 71, enter, is 4.15 when we round it. 4.15. Oh, 14. Sorry. Okay, radicals. So numbers like square root of 52 and cubic root 71 are examples of radicals. So review from last year, remember the little number that tells us the type of radical. That's our index, our radical symbols here, and inside is what we call the radicand. The whole thing is called a radical. The index is not written when it's a square root. It's assumed to be 2, right? So if we had square root of 9, the index here is 2. It's an invisible 2. We don't actually write that little 2. Okay, so next one, this guy, what's his index? His index is 3, and the radicand is the number underneath the radical symbol, 123. Index, if we can't see it, is 2, radicand 77. And index here is 3, and the radicand, what's underneath the radical symbol is negative a half. Using your calculator, do the following calculations and complete the statements. So we're going to type this in. So with our calculator, the square root of 25 times the square root of 16, and then we're going to type in square root of 25 times 16 under 1 square root, and they're equal to the same thing. So this one's our equal. Next one. The square root of 25 divided by square root 16, and then square root of 25 divided by 16, close the bracket, and those are equal as well. Let's try plus. So a quick way to change, if I go second enter, and second enter again, we bring back the previous things we typed in before. So I'm just going to change this to addition, 9, okay, and then I'm going to go second enter, and so just change this to addition, and those are not equal. 9 does not equal 6.4, so not equal. Do the same thing with subtraction. So second enter, so we have the subtraction there, and then we also want to do this version, subtraction, and those are not equal as well. Okay, so these rules only work for multiplication and division. And so the product or quotient of the roots of two numbers is equal to the root of the product of the two numbers. So in general, this is our rule, right? And we use that to simplify radicals. So let's look at this. Is this true? State whether it's true. Is root 16 times root 3 equal to root 18? Well, this is also equal to root 6 times root 3, which is 18. So yes, that is true. So that's true. How about this one? Is there a rule for addition? No, so this is false. And how about division? Can we actually divide these? Yes, we can put them all under 1 square root. And 60 divided by 6 is 10, so this is true. So it works for addition. It does not work for addition subtraction, but just products and quotients. So let's review entire radicals and mixed radicals. So it says write each to 5 decimal places. Oops. So square root of 48 is equal to 6.92820. Okay, we type in 2 root 12. That's again the same thing. 6.92820 and 4 root 3. And again, the same thing. So these are all the same thing, just written different ways. So they're all equivalent. So they're all the same. So root 48 is what we call an entire radical. Okay, the other two are mixed. Now only one of them is fully simplified, and the fourth root 3 is fully simplified, and we're going to talk about why in a second. So we're going to use this rule. So root 48, we could write it as 4 times 12. So root 4 times root 12, and what's the square root of 4? It's 2, so 2 root 12. We could also write 48 as 16 times 3, so root 16 times root 3, and what's the square root of 16? It's 4, so 4 root 3. Now, the second one is fully simplified. And the reason why is there is no perfect square that we can divide into 3. Whereas 12 here, you can actually divide 4 into it, which is a perfect square. So we're going to talk about fully simplified more in a moment. So root 48 is an entire radical, and the other two are mixed radicals. So radicals expressed in the form nth root of b are examples of entire radicals, and the ones with a coefficient in front are called mixed radicals. So how do we convert an entire radical to a mixed radical? Well, this is where we want to use, this is that perfect square chart. So this is, remember, we want to write that down on our study sheets and have it available. So 20 we can break into 4 times 5. Now why would we want to use 4 times 5? If you look at the factor tree for 20, 4 is the only perfect square factor, right? Of all these numbers, 4 is the only perfect square factor. Sorry, should be on the right side. So looking at, these are our perfect squares. And so 4 is the only perfect square factor. And so that's why we're going to break it into root 4 times root 5. And so we can separate that. Square root of 4 times square root of 5. What is the square root of 4? It's 2. So 2 root 5 is the same thing as root 20. So let's look at 72. So when you look at 72, we have our perfect square. So this little chart here, I'm going to go back to it. This perfect square chart, you're going to want to have this handy. Okay, this is going to be handy. So I'm going to actually bring that with me. Take a picture of it. And so I want to keep this with me, because that's going to come in handy for all our questions. So let's bring that over to the next page and paste it here. Okay, so looking at 72, if we take our calculators, and so the first perfect square number, so we're looking at this side of the chart. Okay, those are our perfect squares. So the first number that's actually smaller than 72 is 64. So 64 doesn't go into, 72. Okay, so I try 49. 49 doesn't go into 72, but 36 does. 36 times 2. And so we always want to have one of them being a perfect square. So we can rewrite this as root 36 times root 2, or what's the square root of 36? It's, look at the number here, 6. So 6 root 2. So you could have also broken into 4 root 18, and then that's 2 root 18, and then break down the 18 is 9 times 2, which is 3. Root 9 is 3, and 2 times 3 gives you 6 root 2. So notice the difference if we took the long way, because 18, there was still a perfect square factor that will go into 18, and so you have to break it down even more. So to avoid going through all these multiple steps, if we find the largest perfect square, then we're done right off the bat. So let's try root 160. So the square root of 160, we want to look, okay, what's the largest perfect square that goes into 160? So with 160, you can start, the first number I see smaller than it is 144. We can start dividing by the perfect squares. Now, if you know your times tables, then some of these are going to be obviously, won't go into it, and you'll be able to figure that out on your own. Otherwise, you can just keep dividing until we find the largest perfect square that will go into 160. The other option is making a factor tree, so I'll show you that in a second. So we're 81, next is 64, nope, 49, 36, keep going, so 25, nope, and then 16 is the first one. So root 16 times root 10. So we're going to break this into root 16 times root 10. So the other option is you could have made a factor tree. So 1 times 160, 2 times 160 divided by 2 is 80. Right, so start by making a factor tree. So 3 goes into it. Nope, just 4. 4 times 40. So 4 is a perfect square. But is there a bigger one? So keep going. 5 goes into 160 32 times. 6 goes into 160, does it? Let's check. Nope. So we try 7, we try 8. At 8 times 20. Then we try 9, 9 won't. And then we try 10, and 10 times 16. And now we're done, because 11, 12. We can double check. Does 11? No. Oops. that, no, then 12, no, and 13, and now we're back to 16, so we're done. Okay, so back to 16. So what we have two perfect squares here. We have 4 as a perfect square and 16, but you always want the largest perfect square. So 16, so 16 times 10. So this can take a lot more time than going through your chart. So it's really up to you. So now that we wrote it as root 16 times root 10, what's the square root of 16? It's 4, so 4 root 10. And now it's fully simplified. So next guy, 3 root 98. So 98 is who we need to break down. So we want to find the largest perfect square that will go into 98. The first number smaller than it is 81. So then we'll try 64 and then 49. And 49 is our go-to. So we're going to write it as 3 times root 49, put the perfect square first, times root 2. And what is the square root of 49? It's 7. So we get 3 times 7 times root 21. What's 3 times 7? It's 21. So 21 root 2. And there's our answer. Now it's fully simplified. Now the great thing is you can check your work with these answers because I can type in my original, 3 root 98, square root of 98, and we can type in 21 square root 2, and they should be the same decimal, right? We're just changing its form by simplifying it, but not actually changing the number. Okay, so the distance theorem, this is a formula for calculating distance between 2 points. And it's based on Pythagoras. So it says determine the exact length of the line segment. So we could also make a triangle and use Pythagoras. Okay, so here's our triangle. So our C value, remember, is opposite the right angle. We're trying to find that out. Now I know I went 3 units up and 1, 2, 3, 4, 5, 6, 7, 8, 9 units to the right. And so we can use Pythagorean theorem. So C squared is equal to 9 squared plus 3 squared. So 9 is 81 plus 9. So we get C squared equals 90. And it says answer as an exact length in simplest mixed radical form. So no more decimals here. So we want to simplify 90, root 90, square root by both sides. So looking at our perfect square chart, oops, right here, pull that down. What's the largest perfect square? So here's my perfect squares that will go into 90. Into 90. And I think you might be able to spot it. It's 9, right? 9 times 10. You could also use your calculator and break it through. So we can also write this as root 9 times root 10. And what's the square root of 9? It's 3. So 3 root 10. Okay, so using Pythagorean theorem is a very legitimate way to solve this problem. And you don't have to learn the distance formula. So I'm going to say that when you get to a homework question, you can just skip the part that says use a distance formula. Why don't you use Pythagorean? If you want to use a distance formula, you can, but you could also just use Pythagorean theorem, but you might have to draw it out to use Pythagorean. The distance formula is basically if we have one point, x1, y1, and at one point, move this guy off so you can see the other point, is x2, y2. Okay, so the distance formula says it's really Pythagorean theorem. So we're subtracting our x's, get the difference of our x's to figure out that change in x. So 3 is my x2 minus negative 6 squared plus y2 is 1 minus negative 2 squared. Now remember, if we subtract a negative, it becomes plus. And so this is where we get 9 squared plus 3 squared, which again gives us 81 plus 9, or root 90, which is 3 root 10. We've already broken it down. So this is the end of the first part of the lesson. And so this lesson is broken into 2 parts. So at this point, the homework would be numbers 1 through 7.